the probability of randomly choosing 3 people, 1 from the US, 1 from China, and 1 from Russia with the same blood type? And this is where it gets a little complicated. Because in order for them to have the same blood type, that means that it's the probability that all of them were O, which is what we just found out up here, or the probability that all of them were A, or the probability that all of them were B, or the probability that all of them were AB. That is the general idea of what we want to talk about. We found the probability of O. What is the probability that all of them are A? Well, all of them having A is 0.41 times 0.27 times 0.34. Sorry, that's me. Somebody's messaging me. So I need to multiply all of those together. 0.41 times 0.27 times 0.34, and I should get 0.037638. So a very small percentage, almost 4%, but not even quite that. And then the probability of B, if we go back to our table on the previous page, notice that we are missing one of our B's. It's from Russia, but we have all of the other probabilities. So remember that we just need to subtract these guys out from 1. So I would do 1 minus 0.09 minus 0.34 minus 0.39, and we should get our question mark probability there, which ends up being 0.18. So the probability of B is 0.12 times 0.26 times 0.18, which is 0.005832. The probability of AB is all of the AB probabilities multiplied out. 0.04 times 0.13 times 0.09. Very small probabilities, results in less than 1%. Less than 0.5%. It's a very small probability. Okay, so we found all of these numbers, right? And this is all just the probability of every single one of them being A, the probability of every single one of them being B, and the probability of every single one of them being AB. So now we need to take all of these, where it was this, China and the US and Russia all had A, so the multiplication with this idea of and. Now it's, okay, well, it could be O, or it could be A, or it could be B, or it could be AB. So there's all those options there, which means that we now need to add all of these together. Go ahead and do that on your own. The probability, if you did it to 3 significant figures, should be 0.104. The rest of the digits are 0, 3, 1. But 3 sig figs is totally fine. I just added this and this and this and this. All right. It is estimated that 17% of computers bought from one computer manufacturer require 1 repair job during the first month after purchase. 7% will need repairs twice during the first month, and 4 will require 3 or more repairs. Now, this is not 1 or more. This is specifically these people got 1 repair and done. Right? These people got 2 repairs and done. So there's no overlap here. They are completely independent. Okay, so what is the probability the computer chosen at random from this manufacturer will need no repairs? Which means I need to take 100% and subtract out the probability of any repairs. Well, that's 1, 2, or 3 repairs, right? Those are 3 different probabilities. 1 or 2 or 3 repairs would fall under here. Which means I need to do 1 minus the probability of 1 or 2 or 3. Which means I need to subtract all of those percentages out. 1 minus 0.17 plus 0.07 plus 0.04. All I did was convert these percentages into decimals down here. Subtracting them all out, you should have gotten 0.72, which is a very high percent. And it says probability, not percent. So here's your probability. That's a pretty high probability that you won't have to have a repair, which is nice. We want to have a high probability there. No more than one repair. That's the probability of no repairs or the probability of one repair. So that could be tricky, is that it could be no repairs. No repairs could absolutely satisfy it. Well, we found no repairs. It's 0.72. And the probability of 1 is 0.17. Adding those together, we should get 0.89. Some repair. Some repair is the probability of 1 or the probability of 2 or the probability of 3. We are adding those all together. Adding them all together, we should get 0.28. If you buy 2 computers from this manufacturer, what is the probability that neither will require a repair? So you have the first computer. So let's have comp 1 be first computer, no repairs. Comp 2 will be second computer, no repairs. So if you bought 2 computers, what's the probability that neither of them will require a repair, which means it's the probability that comp 1 will not receive a repair and the probability that computer 2 will not need a repair. So it's this idea of those probabilities being multiplied together because neither of them can get a repair, which means that we're getting a little bit more picky, right? The more computers that we buy, the likelihood that one of them will need a repair goes up, right? We all understand this logically. It's about making sense of the logic to therefore understand the mathematics behind it. But you can all take a step back and say, does this make sense that this number would be getting smaller as this situation goes further? Once I buy 3, 4, 100 computers, maybe I'm buying computers for a school, right? Then that means that the likelihood that one of them, at least one of them, is going to need a repair goes up and up and up. So the likelihood that none of them will need a repair is going to go down, down, down. Remember that the probability that there will be no repairs is 0.72. That is true for both of these probabilities. Both of them are 0.72. Both of them are their own independent event of this one needing no repairs and this one needing no repairs. So that's 0.72 times 0.72. That results in 0.5184. So about 52% likelihood that neither of them will need a repair. So just over half. What is the probability that both will need some repair? So we'll have comp C1 be first computer, needs some repair. C2 will be the second computer, needs some repair. And we found that up above, and so hopefully you're seeing the pattern now, is that both of those will be 0.28. So if both of them will need some repair, that means that the first and the second will have some sort of repair. Whereas if they had said, what's the probability that one of them will need a repair, then it starts to get a little bit more complicated. But since it says both of them will need some sort of repair, you take the probability of some repair that we found up there and say probability of C1 times probability of C2, which is 0.28 times 0.28. That results in 0.0784. Pretty small. Notice that these two do not add up to 1 because those are not all of the situations that could happen when you're buying a computer. When you're buying 2 computers, maybe the first one needs a repair and the second one doesn't. Maybe the second one needs a repair and the first one doesn't, right? So you've still got quite a few situations that you haven't accounted for here, which is why these two probabilities don't add up to 1. But once you account for all the different situations, then it would add up to 1. Okay, The idea of and versus or. And gets more specific, right? And is like we have to fit all of these requirements in order to satisfy this probability, which means it's a very small likelihood that we will satisfy that probability. So and is multiplication because that probability gets smaller and smaller and smaller. Whereas the word or, well, you could be a sweater, or you could be a jacket, or you could be a pullover, and you would still fit the requirement. So then your probabilities are getting bigger and bigger and bigger because your options are getting more and more and more. So or is adding because your probabilities get larger, and is multiplication because your probabilities get smaller and smaller. Great job today.